Okay, so in this video, we will be talking about a very important topic in the world of fluid mechanics. So, there is a special type of flow called vortex flows, and vortex flows refers uh, vortex flows refer to those type of flows which shows rotation or actually not rotation. I should say that uh, it will be uh, it will be better to say that the fluid particles will revolve around a particular axis. That is, the fluid particles will follow a circular path. So why not rotation? So in fluid mechanics literature, rotation means rotation about its own axis. If that is the case, then we say that the fluid flow is rotational. Okay, that is the curl of V, that is the curl of V is not equal to 0, and that implies that the fluid flow is rotational. Okay, and if curl of V is equal to 0, that means the fluid flow is irrotational. Okay, now let us, so as I have said that the concept of rotation, okay, so rotation means what? If I say that I am concerned about rotation, then it is talking about rotation about its own axis, right? Its own axis. Now if I am talking about vortex flows, okay, that that only means, so this terminology only means the fluid particles are following a circular path, right? Okay, now, so if the fluid particles are following circular path, then it has two options. So one option is it can rotate about its own axis, right? Can rotate about its own axis, and uh, so it will not rotate. Next option, it will not rotate about its own axis, right? So if this is the case, the first one, then it will be called a rotational vortex, or what we call as a free vortex, sorry, forced vortex, extremely sorry, forced vortex. Okay, and if this is the case, then it is called an irrotational vortex or a free vortex. Okay, so this is what the basic difference between the concept of rotation and the concept of vortex flows. Okay, so now let us study each type of vortex flows. So forced vortex. Okay, so the practical examples of forced vortex um, can be, so if you are maybe washing clothes in a bucket, then to mix the detergent with water, okay, uh, you can uh, you can give a whirling motion to the water by your hand, and that is what that and I mean that is what a washing machine does, right? So the example is washing machine. Okay, so that is a forced vortex. So mathematically defining a forced vortex means v theta is is proportional to the radius, and so we say c into r, and v r equal to vz equal to 0. Okay, so essentially we will, I mean, as it is a rotating motion, uh, okay, so let's not use the word rotating, let us use the word revolving. So as it is a revolving motion, let us use the cylindrical coordinate, that is r theta z. So v theta, so if I am having motion like this, okay, so the motion is in this direction, so this is my origin, okay, so this is maybe er, that is unit vector along r, okay, uh, in the plane of the paper, or the, I mean, out of the plane of the paper perpendicular to the board, that is ez, okay, and perpendicular to both the directions we have e theta, okay, we have e theta. So this is how we define the r theta z. So e theta is essentially at this instant of time, e theta is in this direction, okay. So that is now, so v theta is equal to cr for forced vortex. R is the radial position of the fluid particle. So vortex flows are something, I mean, which is defined by the uh, uh, which is defined by the revolving fluid particles, right? So they must revolve around about a particular axis. So the distance of that fluid particle from that axis is the r, okay. So this is the forced vortex. Now let me define the free vortex beside the forced vortex. So this is the free vortex, okay. So the example of free vortex, let me tell you, that is a uh, wash basin, okay. So if a basin is having this kind of flow, I mean this kind of structure, okay, so then the water will follow this kind of path, right? So this is a free vortex, and the mathematical description is v theta is inversely proportional to the radius, and again vr vz equal to 0, okay. So now hmm, so now let us, I mean, I have already defined that that free vortex is irrotational and forced vortex is rotational, but still let us calculate the curls, okay. Now curl, that is Nabla operator in e theta z. Now these are something that depicts no glory, if you can remember this, okay. So you will remember this by your own experience, even I don't remember these things. It is the expression of this nabla operator in r theta z coordinate. So this will be er, and this is written by r into e theta, and this is z. Okay, so this is given by this del del r, uh, del del theta, and del del z, and this is v r, r into v theta, and what, so this is vz. Okay, so you can check this after you have watched the video. Okay, so I mean, in the end of the previous video, I just introduced with, I just introduced you with the uh, vortex flows, but in that video the mathematical part was not correct. Okay, I mean, I think I have mentioned already that I don't remember the expression of the nabla in r theta z coordinate, and I have seen that in the internet, and then I am writing this expression. Okay, so the main physics is that you have to understand the physical significance of the curl of v. Okay, that is the main physics, and sorry, and uh, all the concept lies in that. Okay, so I mean, any formula that you can get easily from the internet. Okay, but what lies, the speciality that lies in a human mind, that I think at least till next 50 years AI will not AI will not also be able to track or copy, is the innovation, or the uh, critical thinking power. Okay, so uh, in the earlier days, if a person can do a lot of computations, a lot of complex algebra, complex integration or calculus, that was I mean that was really an incredible achievement. Okay, so but nowadays you can do those things by softwares. Okay, there are a lot of softwares, and AI is also capable of doing such things. But to judge a fluid flow, or maybe to judge a CFD result, you must know the essential physics of the fluid mechanics, the subject fluid mechanics. Okay, so the concepts will uh, so the the concepts will be remaining pivotal. Okay, in every part of life. So uh, now you can check this expression of nabla from internet. Now let us proceed. So this will be 1 by r er into, so del vz del theta, it will be anyway 0 because vz is 0. Okay, now, and r into v theta del del z, so neither r nor v theta are functions of z, so again 0, so minus r e theta into del vz del r, that is 0, and minus del vr del z, that is also 0, plus ez into del del r, so this will remain, so del del r, r into v theta, so that will be c r square, right, minus del del theta of vr, so vr is equal to 0. So this will be directly 2cr by r equal to 2c. So curl of v equal to 2 into c, and in the previous video we have seen that it is nothing but the 2 into angular velocity. Okay, okay, so 2 into angular velocity, that means this constant c is is nothing but the angular velocity, right? So this forced vortex is like, I mean, it is analogous to the rigid body rotation. Okay, so it is analogous to the rigid body rotation, and there is a problem in which we have to find the equation of the free surface, so that we will do later. Okay, now let us move forward. Forced vortex. So after studying the Euler equation, we will be studying the equation of the free surface. Okay, I mean, before also, before studying the Euler equation also, we are in the stage of deriving the equation of the free surface in case of the forced vortex. So you can, I mean, for everything you don't have to uh, take the help of math. Okay, I mean, you have seen it in your daily life many times. So if you have a bucket like this, right, and if this is the axis, okay, and you rotate the bucket like this, and you have water, okay, you have water inside the bucket. So then after the rotation, I mean, during the rotation, it will attain a free surface like this. You can do it right now also. You can have a mixie and you can see it. So you will not see a clear cut paraboloid, but you will see a shape like this, and this is an an actual paraboloid. Okay, but due to the instabilities and disturbances, it is hard to track, right? So now let us uh, go for the uh, curl of V in case of a free vortex. Okay, so for a free vortex, what will be the change? The only change will be, okay, the same thing will be there. So this term, so Vx, I mean Vz and Vr is 0, so this will be 0, this will be 0, and here we will be having, so I am just writing the Ez component because that, so that is what that will remain, right? So I mean, that is the only term that will remain. So Ez 1 by r into Ez into del r, okay, into r into c by r, right, minus 0. So this will be cancelled out and c is a constant. So this is 0. Okay, so curl of V for free vortex is 0. Okay, now let us learn another terminology regarding this vortex flows. So, so that is something called circulation. Okay, so now what is circulation? Circulation is mathematically defined, that if you take a closed contour, okay, if you take a closed contour, use another color, this, if you take a closed contour, then circulation is defined by the that contour integral over the c v dot uh, dr. Okay, so this is the circulation tau. Okay, that is, if you take a closed contour, then uh, maybe you are having an infinitesimally small dr, so this is maybe dr. Okay, sorry. So maybe this is the direction of dr. Okay, so this is dr, and I mean this is the direction of traversing the path, that is this. Okay, and maybe something, some vr you are having, so maybe this is the vr at this position, vr, not vr, only v. Okay, so okay, so this is v. So the integral of v dot dr over the closed contour, so this is called as circulation. Now you have to choose a traversing direction. So the magnitude of circulation is what about which we are concerned, and not the direction. Okay, so if you travel in this direction, then this v dot r will be negative, and because now I mean the direction of the r will be in this side, right? But if you travel in this direction, it will be positive. Okay, so mainly the magnitude of circulation is uh, the important part, and if you maintain a convention throughout the analysis, that is enough. Now, so v dot dr is called circulation. So first of all I would like to okay, so let us calculate the circulation for an infinitesimally um, I mean for let me draw it, for forced vortex. Okay, so uh, let us take the, so if this is the axis and we are taking any contour, so we can take any contour, so I am taking a contour like this, right? I am taking a contour like this. So let me highlight it by another color, maybe this color is good. So this is my contour. Okay, okay, so the center is o, this is a, this is b, c and d. Okay, and I am traversing through this direction. Okay, so this is forced vortex, and maybe this is, so hmm, so this is what is r, small r, and this is r plus dr. Okay, r plus del r itself. Okay, so now here through this line AB I have velocity v theta, so this will be c into r, and for through this line CD the velocity will be v theta equal to c to r plus delta r, right? And during BC the velocity is already 0 because Vr is 0. Okay, so this will give me that Cr into, okay, so this angle is d theta or del theta maybe. Okay, so this is del theta, so Cr into r del theta, right? Because so I mean if the direction of the rotation is this of the fluid. Okay, so in AB the direction of traversing and rotation are same, so the dot product will be positive, right? And now CD, that will give P minus of, because these are opposite. The the direction of rotation of fluid and the direction of traversing are opposite. So this will give v theta into this thing, right, into del theta obviously. So this is cr square del theta minus, so c del theta into, so r square plus delta r square plus 2r delta r, right. I hope I am not doing any mistake. So c theta we can take common, c del theta, so r square minus r square. So these terms, I mean this delta r are very small, so we can neglect it. Okay, so this will be 2r delta r, right, minus of, okay. So c delta theta minus of 2r delta r, okay. Okay, and we can write this as, okay, 2 cr, right, delta theta delta r, okay. So this is the circulation for forced vortex, okay. Now let us do one thing, that is, what is the uh, so now let us compare one thing, tau by r delta theta, right, delta r, sorry, my battery is about to die, so I have to close today's session a bit early. So this will be 2c, right, and what is this r delta theta del r? So this is the area, because, so this is r delta theta and this is delta r, so this is the area, right, because it is an infinitesimally small strip. So this is the area, and this 2c is nothing but the vorticity curl of v, right. So we can see that this tau by this thing, tau by area, okay. So circulation by area of the contour, a contour, so let me write as a contour, this is equal to vorticity. This is very important, this is very handy actually, okay. And this we can prove by a very well known mathematical theorem also, that I will show. Now let us do the same analysis for the free vortex. So I will have the same figure, so let me do it side by side, okay. So for a free vortex, right, so for the free vortex the same calculation will boil down to c by r into r del theta. So this is for the part AB, minus c by r plus del r into r plus del r del theta, right. This is for the part CD, and for the part BC and AD VR is 0, so, and so those will not contain anything, okay. And also if we, okay, so this will be what, this will cancel out, this will cancel out, So c delta theta minus c delta theta, that is equal to 0. So here circulation is coming as 0, so circulation by area of contour, that will be also 0, that means, and that is equal to vorticity, and vorticity is 0, that we have seen earlier. Okay, now let us take the contour. So these two calculations are valid for the contour what, a b c d a. Okay, for this contour these two calculations are valid. Now let us take a contour o o d c o. Okay, that is this contour we are traversing like this from D to O, then from this to this, then from this. So now let us do it for the free vortex. Okay, so for the free vortex, if we do this now, so for OD and OC there can be VR, but VR are 0 and V theta are perpendicular to the paths, so the dot products are 0. Okay, and same for the VZ, although VZ is also 0, so those will be 0. And for the path CD, okay, for the path CD we will be having what, uh, C into R plus, okay, so C by R plus delta R into R plus delta R into del theta, right? So this is for the path CD, the same expression, right? And plus 0 for path OD, I mean DO. So we are traversing like written the incorrect sequence, it is DOCDO. Now this is correct. So for DO and for OC the circulations are 0, right? So this will come as C delta theta, and this is non-zero, right? So as, so then it contradicts, right? That for one contour we are getting that the flow is irrotational, and for the other contour we are getting a non-zero circulation, that means the flow is rotational. So where is the catch? The catch is at O, okay, at O, so let me write it here. So at O for free vortex velocity is what? V theta is, okay, uh, C by R at R equal to 0, and that is not defined. Okay, so you cannot take any point which is a singular point. So here this R equal to 0 is a singular point for the free vortex. So there is a criteria for the selection of the contour whenever you are calculating the circulation, that is you cannot take any point, you cannot take any contour which contains a singular point. Okay, so let me write it. So you cannot take any point which contains a singular point. I apologize, you cannot take any contour, okay, during calculation of circulation. Okay, so this you have to keep in mind. Now let me talk about a very important theorem that is called Stokes theorem in vector calculus. Okay, so Stokes theorem. So Stokes theorem says that if we have, okay, if we have a vector, let us say A, so A dot dr around a circle, so around a contour C, that will be equal to, sorry, that will be equal to area integral, so curl of A dA, and this A will be A of C, area enclosed by the contour. Okay, now put A equal to V, the velocity vector. So if you put this will give what? A cyclic integral of V dot dr is equal to curl of V into dA, right, and area enclosed by the contour, and that directly gives cyclic integral, not cyclic integral. So this is directly the circulation, and that is equal to vorticity. So let me denote this by this. So vorticity vector dA. Okay, so this is, so this dA area is also a vector. Okay, and some says that area is not a vector, area is a scalar, and area multiplied by its own normal is a vector. So I am okay with any of the concepts. So if someone disagrees that I cannot write it like that, sorry, then I should have write like n, so this dot nda, right? So then you can write this also. Okay, so this will be dot nda, right? Okay, and if the vorticity is constant, that is the vorticity is not a function of the area, okay, it is constant along throughout the whole area, then we can take out the vorticity, and this will give us area of contour equal to vorticity vector. Okay, so this is the concept. Now we can see that a simple, I mean not simple, a very brilliant mathematical theorem of vector calculus that boils down to the concept of a fluid mechanics. Okay, so essentially fluid mechanics was a subject for mathematicians. uh, okay, so if you study the history of development of fluid mechanics, it was essentially the topic of pure mathematicians. Okay, so there are very famous books written by mathematicians on fluid mechanics. Okay, so all the concepts of vector calculus, those if we put the velocity vector instead of the vector notation in the vector calculus theorems, then all the concepts will get some significance in terms of fluid mechanics, all the, I mean all the formulas of the vector calculus. So if you are aiming for gate, so then you don't have to remember Stokes theorem separately. You just remember that I know that vorticity is equal to uh, area into, I mean vorticity is equal to circulation by area. Okay, so just think about it, that means circulation means V dot dr, and it's cyclic integral. Okay, and essentially if now if I have to match the dimensions, then I can write it that this is equal to my vorticity into area, as simple as that, and this is curl of V into area. So this is like the, I mean this is one of the tricks by which you have to only remember that uh, that there is a relation between the circulation and vorticity, and that boils down to the Stokes theorem. Okay, So for me it was easier to remember the I mean the relationship between the vorticity and the circulation. Okay, and now I am uh, I mean I can recall the Stokes theorem itself, but when I appeared for GATE, it was hard for me to remember all the formulae of vector calculus. So I used these types of tricks, I mean, which comes from the fluid mechanics concepts. Okay, just like that, we can correlate the Gauss divergence theorem, we can correlate the Green's theorem. So Green's theorem is nothing but the 2D form of the Stokes theorem. Okay, so like that you can generalize, I mean, all the formulae. Okay, and you can correlate those formulae with the concepts of fluid mechanics that will make your task easier. Okay, so maybe you are a guy who can remember the formulae better than these concepts. Then if you can remember the Stokes theorem, then you can easily remember the relation between the circulation and the vorticity. Just put velocity in the Stokes theorem, right? So these are the tricks, I mean, the tricks that originates from the scientific concepts. Okay, and this also shows that everything is connected. Okay, I mean, even in mechanical engineering. So let me give you another analogy. Okay, so in heat transfer, so we have studied the Ohm's law and the theory of the networks, the electrical networks. So if you can find that the heat transfer, in the heat transfer, if you can find the same law that will be analogous to V equal to IR, then you can also apply the same theory of electrical network. And there is a chapter that is named as the analogy between thermal and electrical network, right? So these are the connections between the uh, different streams of the same subject, mechanical engineering. Okay, likewise you can find many other analogies uh, between the topics of different subjects, be it heat transfer, be it fluid mechanics, be it uh, solid mechanics. Okay, so there are analogies, there are, I mean, tremendous and very helpful analogies between solid mechanics and fluid mechanics. Okay, these two are essentially the branch of the uh, continuum mechanics. Okay, so these two must have some analogies. Okay, so with this let me stop for today, as my battery is almost dead. Okay, so, and if you have any suggestion and any comments, or if you have any doubts, just post it in the comment section and I will surely answer it. And let me remind you that just ignore the mathematical part of the vortex flows in the previous video, as I did not recall the actual expression of the nabla operator in r theta z coordinate. I think I have mentioned it in the previous video also. The explanation, the physical explanation, that was right, only the mathematical part that you should ignore. Okay, because I don't want that you learn anything wrong because of me. Okay, so I always encourage that if you find anything wrong or illogical in my video, then you should tell me, right? Then you should tell me, I will accept that and I will correct it in my upcoming videos. Okay, because I am also learning and you are also learning, so let us learn together. So thank you, and so let us meet in the next video. Take care and bye.